Once you've got the charge separated, there are two ways to monitor the signal coming from the detector. One thing we can do is just measure the current itself produced by the ionization of the gas by the radiation. This strategy is used in ion chambers. The instruments that health physicists wave around in front of them when they measure dose is a gas-filled detector, and the current from the sensitive volume can be related fairly easily to dose. For identification of nuclides, current mode is no good. We use pulse mode, the other way, to monitor the signal coming from the detector. And we look at the signal in detail that comes from each ionizing event in the detector. All the instruments used in this class will be operated in pulse mode because it preserves the information on the amplitude and timing of individual signals. If you stare at the electronics here for a minute, the important parts in the collection electronics is the capacitor and the resistor. The product of the capacitance times the resistance, the RC constant, has a profound influence on the shape of the signal coming out of the detector. Let's talk about that. We will end up measuring the time-dependent voltage across the resistor R. If the RC constant is very small, then the voltage is essentially the same as the current, and it will faithfully track the charge collection as it takes place in the detector. If the RC constant is large, on the other hand, it creates a long tail in the signal because the voltage initially charges the capacitor, and then the capacitor slowly discharges to cause the tail on the signal. At first, you might think this would be a crummy way to go, but it turns out this is exactly what we do. We almost always use a large RC constant because the electronics are much simpler, and the redeeming feature of this whole thing is that the amplitude of the maximum voltage is equal to the total charge collected divided by the capacitance. So instead of having to integrate to get the total charge placed in the detector, we simply measure the maximum voltage of the pulse. Thus, the rate at which pulses are created is proportional to the radiation interaction rate, which is proportional to the radiation emission rate. The height of each pulse is proportional to the amount of charge put into the detector, which is related to the energy of the incident radiation. It is these two characteristics that allow us to measure the energy spectrum and emission rate of radiation from a source and allows us to identify and quantify the source.